So the evidence to support the distribution of electrons according to the alphabet order comes from something called photoelectron spectroscopy. So if you break that word down, spectroscopy we've seen before, that refers to looking at a range or a spectrum of values of measurements and being able to visualize those. And the photoelectron part, if you break that word down, photo meaning light and electron, pretty self-explanatory there. So we're going to be dealing with electrons and light, which is energy, and looking at the spectrum of different energies that are presented. So to begin this, let's think of a little analogy. Let's say we've got a soccer ball that's sitting at the bottom of a ditch, and in order to get it out of that ditch, we can see that we need 45 joules of energy to be able to release the ball from the ditch. So our soccer player there is going to kick that ball, and if they think about what's keeping the ball in the ditch, all right, it's going to be gravity. Gravity's holding it down there at the bottom of that low-lying area. And so the type of energy it's going to be needed to move the soccer ball out of the ditch, keyword move there, is kinetic energy. And so if we think how much energy is going to be needed, then that's where this 45 joules comes in. So what happens if our kicker applies 30 joules of energy to the ball? Well, as you might expect, it'll travel part way up, maybe about 2/3 of the way up, but then it runs out of energy, and it's not quite to the crest of the hill, so it's going to roll back down, and it stays in the ditch. If our kicker applies 45 joules of energy, well, that's exactly the amount that's needed, so it will hit the top of the ditch, but then as soon as it hits that lip, it's going to stop because there's no additional energy to be imparted on the soccer ball. If our kicker really winds up and applies 60 joules of energy to that kick, well, the first 45 goes towards getting that ball up to the top of that ditch, but then once it's free of the ditch, it still has some extra leftover energy. And so the ball reaches the top of the ditch and it keeps going. And then when we think, okay, well, it's moving, so it's still got kinetic energy. How much? Well, it used 45 of the 60, so that means there's 15 joules of energy left over. And that would be the kinetic energy of the soccer ball as it progresses. So if we think about the relationship between how much energy the player put into the kick and the potential energy of the gravity that's holding the ball in the bottom of the ditch, and the kinetic energy of the ball after it's left the ditch, if we think about those three in combination with one another, the one of those terms that is most analogous to the total is the amount of energy that the player kicks with. So if we think, what is the kinetic energy of the kick going to be equal to? Well, that energy was enough to get the ball out of the hole, so overcome gravity, plus the leftover kinetic energy that went into the roll. So kinetic energy kick equals potential energy of gravity plus kinetic energy of the roll. So now let's shift our attention to the same concept, but put it in the context of an atom. So we've got a hydrogen atom, one proton, one electron, and we see we also have a photon of energy coming in and striking this atom. So what's keeping the electron in the hydrogen atom, you may recall, is the attraction between oppositely charged particles in the atom, namely the protons and electrons, and that was Coulombic attractive forces. And so if we want to remove an electron from an atom, we have to provide energy, sufficient energy that's going to overcome those Coulombic attractive forces. And that energy typically comes from a photon of electromagnetic energy. So if we put the two models together and kind of look for the parallels and the similarities, what held the soccer ball in the ditch was the force of gravity. In a hydrogen atom, what holds the electrons in the hydrogen atom are those Coulombic attraction forces. The ball itself would be analogous to the electron, and the kick given by the player to try and boost that ball out of the ditch would be analogous to what's providing energy to the electron to try and get away from the atom, and that would be the photon of light energy. Now that amount of energy that's required to get an electron away from the nucleus, to remove an electron from the atom, is what we call ionization energy. And so if we think in our comparison here, what's going to be analogous to that? Well, the energy needed to remove the soccer ball from the ditch, that was this 45 joules of energy. So if we now take that equation that we had put in terms of the kinetic energy of the kick, the potential energy of gravity, kinetic energy of the roll, and we make the parallel to what we see in the hydrogen atom, the kinetic energy of the kick is what gave the energy, the photon is what's providing the energy here. So the energy of the photon is going to equal the energy that's required to overcome this attraction. Okay, and so that's what ionization energy is. And then any leftover energy is going to be imparted to that electron, and it will carry it out of the atom itself. And so we have the kinetic energy of the photon, all right, coming in. That's equal to the ionization energy, the energy required to overcome that Coulombic attractive force. And then once that soccer ball, electron, leaves, then it's carrying with it a certain amount of kinetic energy. And notice what we call that particle that's leaving, a photoelectron. It's an electron that has been liberated by a photon of light, hence photoelectron. So photoelectron spectroscopy allows scientists to be able to determine what are the ionization energies for the electrons, not just the valence ones, not just the ones on the outside, but any electron throughout the entire atom, even down to the 1s level. And so what happens is you've got a sample, like mass spectroscopy, it's going to be in the gas phase, and you're going to bombard it with lots of X-rays and ultraviolet rays. Now why X-ray and ultraviolet? Well, if you remember, X-rays and ultraviolet rays are higher in energy, lower in wavelength, higher in frequency than visible light. So you want a form of light energy that's going to provide photons that have lots and lots of energy, enough that you know you're going to be able to liberate even the most tightly held electrons, and still have those electrons have energy that can be measured once they are free of the atom. And so using a specific wavelength of light, you know what that incoming energy is, and based on the energy of the photoelectrons coming out, which you can measure and count, then by subtraction you can figure out what was the amount of ionization energy that was needed. What's the difference in those two energies? That difference is going to be the energy that was needed to boost the electron out of the atom. So if we think about a lithium atom, okay, that would be analogous to having a two-tiered ditch, if you will, okay? Two different distances, okay? And we know that the further the distance the electrons are, the more energy the electrons have, and thus the easier it is to remove them because the Coulombic attractive force is weaker. So when we consider soccer player A and B, and which of these electrons they would be most representative of, okay? 3 is the one that's the furthest out. And so it's a higher energy electron, meaning it doesn't require as much energy applied to it to be removed. And so if we look at our two soccer players, we see the one that's on this upper tier only needs 30 joules to get the ball out of the ditch, whereas player A needs 45 still. Okay, so electrons 1 and 2 are closer in, stronger attractive force holding them in, therefore it's going to require more energy. So electrons 1 and 2 would be analogous to soccer player A. Electron 3 would be analogous to soccer player B. So here we see a sample of a photoelectron spectra for the element lithium. Okay, and when we see these graphs, a couple important things to note. First of all, it's going to be the number of electrons that are emitted. Sometimes it might be referred to as photoelectron intensity. May not always have a numeric scale on it, but we'll talk about how you can identify what those, how to kind of make your own scale there. And the x-axis is going to be ionization energy. Now you may also see it named as binding energy. Typically it will be kilojoules or even larger units, megajoules per mole, okay? The other thing to note is the numbering of the scale. If you look carefully here, it's reversed from what you would expect. And so what you want to do is think of the nucleus as being here at the origin. And so therefore, the closer to the nucleus you are, the stronger the attraction is and the more energy it's going to take to remove the electrons. And so that's why it goes typically from higher energy to lower energy. Okay, so that's one thing to take note of. And you always want to double check that too, because there may be, a PES graph where they number the x-axis in a conventional way to kind of test you to see, are you looking for that highest energy peak? And that's what you key off of for the 1s orbital. How many peaks you've got is going to correspond to the number of sublevels that you are going to have your electrons in, and therefore how many you'll see in the electron configuration. The 1s level always corresponds to the highest energy peak that you have. The height of the peaks, in turn, then gives you a representation of how many electrons are in that particular sublevel. And again, knowing what we know about electrons and the Aufbau principle and how electrons fill in, 1s is always the lowest energy sublevel, so that would be the first one to be filled in, and s sublevels only have a maximum capacity of 2. So if you have multiple peaks, you know the 1s level had to be completely filled. And if 1s can only hold 2 electrons, then whatever that intensity is represents 2 electrons. And so what you would do then is compare the other peak's heights to that one, and you can see in this case the second peak is half as high, so we can deduce that there's only 1 electron in this particular sublevel. And because it's the next lowest energy or next highest energy, that would be the 2s level. And so you would have 1s2, 2s1, which is the configuration for lithium. Sometimes in these graphs you'll see a double line somewhere along the horizontal axis, and that's basically just to chop out a wide section where you don't have any peaks recorded. Excuse me. So it doesn't change the way the numbering is. It doesn't change the way that you assign what the labels for the sublevels are or determine how many electrons are present in each one. All right, so here's an example of a PES for potassium. And so the first thing you probably want to do in looking at this is determine what your 1s sublevel is. So we look for the largest energy peak that we have, which is right here, about 347. And so if we know that's 1s, that means right here is going to be 2 electrons. So we can kind of set our own scale, whether you go, 1, 2, 3, 4, or you go by 2s, that's up to you. Okay. So then we want to label each peak with the sublevel it represents. So the highest energy is 1s, and then from there, just follow the Aufbau order. Use the periodic table if you need to. 2s, 2p, notice it's much taller because it has more capacity for electrons. 3s, 3p, and then don't miss any teeny tiny ones that you might have. So this would be 4s, and it's half the height, so you can expect that would be 4s1. All right. So now, let's say this is for elemental neutral potassium. Okay, the question that follows is which electron is going to be removed in order to form the potassium ion with a +1 charge. Well, remember, when we ionize atoms, we always remove electrons from the valence or outermost shell, which means that it's going to come out of this 4s level. Okay, and so it would be 4s. Another way this question could be asked is, what is the energy required per mole to form a mole's worth of potassium ions? And so that would require you looking at whatever the scale is, and here we're given the value. So that would be 0.42 megajoules of energy would be required to ionize a mole of potassium into potassium +1 ions. Right, now on another typical type of question would be to take an existing PES and consider a different element, an element that's very close to the one that's illustrated, and to superimpose where those peaks would be. So in this case, potassium has the atomic number 19, calcium is 20. So if we think about calcium and its 20 electrons, okay, that means it also has 20 protons. And so if you have more protons, think about what that does to the Coulombic attractive force. It strengthens it, which means it's going to take more energy to remove or ionize those electrons. So what we expect and what we see is, in fact, that the peaks would be shifted to the left. I don't have them drawn on here, I apologize for that. But they would be shifted to the left to higher energies, and that last peak, okay, is going to be drawn higher. It's going to be drawn up so that it would be same intensity as the other S sublevels with 2 electrons. Okay, another common type of question. Here's a PES. What element is it? So we look for the highest energy peak that we've got, which is right here about 126. So that's 1s. That's going to be 2 electrons at that height. So 1s2, 2s2. Okay, now next would be 2p, and we see there's another peak even to the right of that, so we know 2p had to be filled. So 2p6, and then the next would be 3s, and it's got the same height as the first 2s sublevels, so it's 3s2. So that means we've got a total of 12 electrons, and so we look for 12 protons, and that would be magnesium. All right, if we consider our shell models that we typically envision electrons being in, and now compare it with PES data, we can see which one is going to be a better representation. All right, in both of these you have 10 electrons, all right, as we would expect, based on what we see here, okay? You've got 2 plus 2 and then 6, so there's your 10. But the key here is that you've got 3 distinct energies, which means you've got 3 distinct levels or distances that those electrons are going to be found from the nucleus. So whereas this might be the more conventional Bohr type model that we think of, first main shell, second main shell, third main shell, there's actually evidence via PES that supports the fact that even those main levels are broken down into sublevels. All right, so again, 2, 2, and the 6, that gives us a total of 10, and so this would be the PES for neon. All right, a couple of interesting things to note here, all right, between phosphorus and sulfur. So again, a comparison between 2 elements that are right next door neighbors to each other. And so we're asked to first explain the difference in the x-axis position of peak A in both of these graphs. And you'll notice for sulfur, it's slightly shifted to the left. Okay, and so if we think about what's different between phosphorus and sulfur, well, sulfur has 1 more proton than it does phosphorus. So it's going to have stronger Coulombic attractive force, pulling the electrons in closer, and therefore it's going to require more energy to remove the electron from that 1s level. All right, so now let's look at the other end, and we look at peak E, and we see in sulfur peak E is taller than peak E in phosphorus. And so the difference there is sulfur's got 1 more electron, so we would expect the intensity in that outermost or lowest energy sublevel to be higher. Okay. And we know that there's space for it to go in there and not just start another level because, based on the progression, 1s, 2s, 2p, 3s, 3p. You know, phosphorus only had 3p2, 3p3, okay? So there is still capacity there. Now, looking at E and looking at the rest of the peaks, notice E's peak for sulfur actually shifted to the right. Okay, sulfur's got 1 more proton, and all the other peaks shifted to the left like we would anticipate, but peak E shifted to the right. Okay, so this is a really neat kind of question, and one that I think is kind of a favorite to ask. You know, why does this happen? So What we have to think about is the electrons that are there, how are they distributed? In phosphorus, you've got 3 p electrons, okay? One in the px, one in the py, one in the pz orbital. So those 3 dumbbell-shaped orbitals, all 90 degrees from each other, those electrons are perfectly symmetrically spaced out. They're as far apart as they can get. When you add that next electron with sulfur, it pairs up in the first, p orbital, the px orbital. And even though it's going to spin down according to Pauli exclusion principle, you still nevertheless have 2 negatively charged, like charged particles, inhabiting very close to each other the same space, okay? And that's not a real favorable situation. Like charges tend to repel. And so what happens is, with the addition of that 4th electron, all right, which now pairs up electrons in one of those orbitals, that repulsion actually causes the electrons to move further from the nucleus. Well, the bigger the distance between the nucleus and the electrons, the weaker the attractive force is, and therefore it takes less energy to remove those electrons. Hence, why it takes a smaller ionization energy to remove one of those 3p valence electrons out of sulfur compared to phosphorus. All right, so we take a look at this one. All right, a couple things to note here. There's a simulated photoelectron spectrum of scandium, Sc, atomic number 21. Here's an important piece right here. The 1s peak occurs at 433 megajoules per mole and is not shown in this spectrum. Okay, so by now, hopefully you're attuned to looking at the scale, looking at the highest energy peak, and you're initially probably thinking 1s. Okay, but even if you miss this, instruction that's clearly there in black and white, when you go to look at your next peak, you should be expecting something that's the same exact height as the first one. We don't have that here. So that would be another clue that would hopefully get you to reread things and note, okay, 1s is way over on the left, and this is actually 2s. And this would be 2p, 3s, 3p, so now that makes sense. All right, but we go beyond that. Okay, scandium ends with 4s2 3d1, so that must be what this little doublet out here is for. Okay, but if you look at the peak heights, it's easy to determine which one's the 4s and which one's the 3d. Okay, the peak that's the same height as the other s sublevels, that's the 0.63, so that's going to be your 4s. 3d is going to be the 0.77. Okay, so now notice what's different about this is up until this point, we kind of had the Aufbau order right in line with the peaks. Here, it's reversed from what you would expect the Aufbau order to be in terms of the ordering of the peaks in the PES. And the reason for that is, remember that the principal energy level number, the principal quantum number, that coefficient gives you an idea of the size. And size relates to the distance from the nucleus and therefore how accessible the electrons are going to be. And the 3D, even though Aufbau order-wise, 3D doesn't fill in until after 4s, the third main energy level, you're going to have smaller orbital clouds. And so those d electrons are going to be a little more interior to the 4s. And therefore, because they're a little more interior, right, they're still higher energy because it's a d sublevel. And you've got 5 orbitals that you're trying to fit electrons into. Because it's in the third main level, you've got shorter distance and therefore stronger Coulombic attractive force and a little bit higher ionization energy. All right, to wrap things up here, think about these questions, true or false, and then be able to justify. The PES of carbon-12 should be identical to that of carbon-13. Well, carbon-12 and carbon-13 are isotopes of each other, and the only thing different about isotopes is the number of neutrons that they have, hence the difference in mass. Well, neutrons have nothing to do with Coulombic attractive forces, and therefore should have no bearing on how much energy is required to remove those electrons. And so this statement would be true. They should be identical. The next question, the PES of tin-2 and cadmium should be identical to each other. Well, tin-2 and cadmium, they're isoelectronic. They have the same electron configurations. However, they don't have the same number of protons. All right? Tin has 2 additional protons than cadmium does, and therefore it's going to have a stronger inward pull on the electrons, and therefore stronger attractive forces, and would require a larger ionization energy to be able to remove those.